the transformer efficiency problems. Okay. Copy the first problem for the day. A transformer working at unity power factor. Transformer working at unity power factor. So power factor is UPF. UPF stands for unity power factor. Has an efficiency of 90%. Has an efficiency of 90% at both 1/2 load and at the full load. Both at 1/2 load and at full load of 500 watts. So let me repeat. A transformer working at unity power factor has an efficiency of 90% at both 1/2 load and at full load of 500 watts. Full stop. Determine the efficiency at 75% of load. Okay. So this is the problem. So try to understand the given data. So in the given problem, what they have mentioned is the transformer is having an efficiency of 90%, both at half load as well as full load of 500 watts. So you can say that, okay, so solve. So eta is equal to 90% at half load, right? And what is the full load value? 500 watts. So here it is given as full load is 500 watts. So 0.5 into 500 watts. And power factor is 1. So basically X is 0.5. Also, the efficiency is 90% at full load. So X is equal to 1 and power factor is unit. Okay. And you need to determine the efficiency at 75% load. So in order to determine the efficiency at 75% loading, what you need is the loss information. Unless or otherwise you get to know about the losses, it is not possible to find the efficiency. So you need to find the loss information. So how do you find the loss information? So you need to find the loss information by considering these two cases. In the first case, you have 90% efficiency at X is equal to 0.5 and power factor is equal to 1. In the second case, you again get 90% efficiency, but for X is equal to 1 and power factor is equal to 1. So consider these two cases independently. All right, fine. So you can write down, given the full load in watts, right? Given that the full load is in watts, right? So full load is equal to 500 watts. But when we write the transformer efficiency relation, normally it's a standard practice to take the full load kVA. But instead of kVA, you have watts. So how will you find full load kVA? So full load kVA can be found by making use of cos phi. So cos phi, okay, that's your power triangle if you recall. This is your kVA, kVAR, and kilowatt, and this is your phi. So find out the cosine angle cos phi that is adjacent by hypotenuse. So kilowatt by kVA. So therefore, kVA is equal to kilowatt divided by cos phi. Okay. So how many kilowatts? Okay. Yeah. In this case, they haven't mentioned kilowatt, they have mentioned watts. So just write 500 watts divided by cos phi. What is cos phi? Unity power factor. So cos phi is equal to unity power factor. Unity means 1. 1. So your kVA or VA rating is basically 500 VA. 500 VA. So this is the general formula. So this is basically P, right? So P, this is Q, and this is S. So this is how you can find out the VA rating, which is S, or you can say SFM. Okay. So once you know SFM, you can apply the efficiency relation. Eta is equal to X into SFM cos phi divided by X into SFM cos phi plus iron loss plus X square times TCU full load. Okay. So this is your expression. Now you can start substituting the two cases. So let's substitute for case 1. So you can write case 1. Okay, what is case 1? 50% loading they have given, right? Half of the full load. So X is 0.5 and power factor is 1. So, and efficiency is 90%. So 90% is 0.9 is equal to X is 0.5 into SFL, which is 500 into cos phi is 1 divided by 0.5 into 500 into 1 plus iron loss plus X square times the copper loss. So it is 0.5 square times full load copper loss. Okay. So simplify. What do you get? It is 250 you will get. 500 into 0.5 is 250. 250 plus iron loss plus 0.5 square. So 0.5 square is 0.25. So 0.25 PCU full load or cross multiply. So when you cross multiply, what do you get? 0.9 into 250, 225 plus 0.9 PI plus 0.9 into 0.25. That is 0.225 PCU full load is equal to 250. Okay. Or you can simplify something like 0.9 PI plus 0.225 PCU full load is equal to 250 minus 225. So that's 25. 25. 25. Okay. So this you can take it as equation 1. So this is your first simultaneous equation. So once you have this equation, you can go for the second case. So here you write case 2. Now in case 2, they have mentioned that X is full load, power factor remains the same, that is unity, and efficiency is 90%. Right? So extend the formula. So 0.9 is equal to X is 1 and SFL is 500. Okay, and power factor is 1. So you will get 500 in the numerator, so as 500 in the denominator, plus iron loss, plus x square, that is 1, x square PCU full load, right? So you will just get PCU full load. Okay. So that implies you can cross multiply. So 0.9 into 500 is 450. So 450 plus 0.9 PI plus 0.9 PCU full load is equal to 500. Or simplify this 450, you can take it on right hand side. So you will get the equation as 0.9 PI plus 0.9 PCU full load is equal to 50. This is your second equation. So you have equation 1 and you have equation 2. Okay. So you need to solve these two equations. You can put it in your calculator or straightforwardly you can calculate. Okay. So I'll go for equation. So you will get the iron loss as 18.51 watts and full load copper loss as 37.03. Okay, so that's your loss. All right, I hope you have got this answer. Okay. I just confirm with the textbook answer. Okay. So this is your loss component of this particular transform. So once these two losses are known, you can find the efficiency at 75% loading and at the same power factor. All right. So next you can write, therefore, efficiency at X is equal to 0.75 and power factor is equal to 1 can be given by eta is equal to X. X is what? 0.75 into SFL, that is 500, into cos phi, that is 1, divided by 0.75 into 500 into 1 plus iron loss plus x square times, right? So x is 0.75, so it is 0.75 square times PCU full load, Right. I'm not writing down the formula because I have already written the formula, and every time I cannot write the formula, it takes a lot of time to complete. So full load copper loss you have calculated, right? So as the iron loss. Iron loss is 18.5. You can directly substitute 18.5. Here let me write. This is Pi. And full load copper loss, this is 37.03. So this is PCU full. All right. And this is your X. Here itself, let me write, okay, so that we can solve more problems. This is your X. And this is your power factor. And this is your VA rate. So please substitute in your calculator and let me know the efficiency answer. How much you'll get efficiency? $90.5. So 90.5 is the book answer. You can confirm whether you have got the same answer or not. So that's the efficiency. Okay. So, all right. So that's your first problem for the day. Second problem you consider. So it's given that 40 kVA, 40 kVA single phase transformer has core loss of 450 watts and full load copper loss of 850 watts. So let me collect the data from the first statement. 40 kVA transformer. So full load kVA SFL is 40 kVA kilovolt ampere. Has a core loss of 450. What do you mean by core loss? Core loss is nothing but iron loss. So iron loss is 450 and full load copper loss, PCA full load, is 850 watts. If the power factor of the load is 0.8, so they have also given you the power factor, which is 0.8. If the power factor of the load is 0.8, calculate first one, full load efficiency. First one, full load efficiency. Second one, maximum efficiency at UPF. Max efficiency at UPF. UPF stands for unity power factor. Third one, load for maximum efficiency. So this is the problem statement. All right. Fine. kVA is given 40. Iron loss, copper loss is given, and power factor is given. So firstly, you need to calculate the full load efficiency. So write down the first object, full load efficiency. So at full load, we know that X is 1. So you can write the general efficiency relation X SFL cos phi divided by X SFL cos phi plus iron loss plus X square times TCU full load, which is equal to, what is X for full load efficiency, or rather for full load, X is 1 into SFL. What is the rating, full load rating? 40 kVA, so 40 into 10 to the power 3 into cos phi. Cos phi, or the power factor, is given as 0.8 divided by 1 into 40 K into 0.8 plus the iron loss 450 plus X square. So X is 1, so it is 1 square. 1 square is 1 into PCU full load. So PCU full load is given 850. So substitute this and try to get the value of efficiency. So how much you'll get efficiency as? 96.096 you should get. 96.096%. So that is the efficiency. Please try to calculate the efficiency. Fine. So that's about full load efficiency. Next, let us consider part number 2. So in part 2, what is that you should do? Maximum efficiency at UPF you are supposed to find out. So second one, you can write. See, there are two ways of solving this. You can in fact first find the load at maximum efficiency, and then you can proceed with the calculation of maximum efficiency. Okay, or you can make use of the condition at which the maximum efficiency occurs. So we have seen that, you can write, we know that at eta max, fixed loss or the core loss is equal to variable loss, right? So P equal to TCU. So iron loss is equal to copper loss. So what you can do is, you can write eta is equal to, or rather eta max is equal to, the expression, full load copper loss, we are finding out the efficiency at full load. So you can directly take it as 40, okay, X is 1, so 40 into 10 to the power 3 into cos phi. Okay, so they are asking you to calculate the efficiency at UPF. So cos phi is 1 divided by X, we are taking 1, and SC is 40 into cos phi plus iron loss. What is iron loss? 450 plus the copper loss. So at eta max, since iron loss is equal to copper loss, you can write the copper loss as iron losses. So this is the crucial step. Okay, so you can substitute these values. Okay, so see what I have done here. In place of copper loss, I have substituted the iron loss. Okay, the lesser loss you have to substitute. You can't substitute the copper loss, because if you substitute copper loss, what happens is that you will not get maximum efficiency, right? So that is the thing. So fixed loss is equal to variable loss. So keep iron loss as 450, but in place of copper loss, you substitute the iron loss value. So iron loss value is 450 watts. How much you'll get?
97.
7.7%. Okay. I hope you understood this point. I'm substituting these two as iron loss. Because if you take, instead of iron loss, both the factors as copper loss, what will happen? Your entire denominator becomes, large. If your denominator value starts increasing, your efficiency starts reducing. So you have to substitute the minimum loss, which is always the iron loss. And always iron losses are lesser compared to the copper loss. Okay. So that's about the maximum efficiency, 97.7%. The third part, which is nothing but the load at which the maximum efficiency occurs. Third part. So we have seen a standard result, right, which we got it from one derivation, that Sm, which is nothing but load at maximum efficiency, is equal to full load, which is SFL, into under root iron loss divided by full load copper loss. So Sm is equal to full load is 40 into 10 to the power 3 into under root iron loss is 450 divided by full load copper loss is 850. So pretty straightforward. So when you substitute, how much you'll get? $29.1. It is 29.104 kilovolt amperes. Okay. Xm, or the load factor for maximum efficiency, is nothing but Sm by SFL. So this value you have to divide by 40 kVA. So it is 29.104 divided by 40. So 29.104 divided by 40. That's about 0.7276. So what is the understanding? If this particular transformer is loaded to, let's say, 72% of full load, then it gives maximum efficiency. So this particular transformer is giving you maximum efficiency when it is loaded till 72.76% of the full load. Okay, so that is the understanding. So you have found the load as well as you have found the load factor, which is 0.7276. Okay, so that's your second problem. The third problem, pretty lengthy it is. So I need your active participation while solving this problem because it's pretty lengthy. All right, fine. Then copy the question. A single phase, 25 kVA, 1000 volt bar 2000 volt, 50 hertz transformer has maximum efficiency of 98%. So they are giving eta max value has maximum efficiency of 98%, that is 0.98 at full load UPF. At full load UPF. Determine its efficiency. Determine its efficiency at 3/4 of full load, comma UPF. Second one, half of full load, comma 0.8 power factor. Third one, 1.25 times full load, comma 0.9 power factor. Okay. So this is the problem. Pretty lengthy it is because you need to handle the three parts. Correct. Right. So how do you solve this? One thing we have understood from our past problem solving experience is that in order to determine the efficiency, you should have the details about the loss components, as in iron loss and copper loss. But in this particular problem, you haven't been given with the loss components, right? There's no information regarding iron loss or copper loss, but you have been given with the maximum efficiency condition. So what you need to do is you need to make use of this maximum efficiency condition to determine the iron loss as well as copper loss. Okay. So solution you can write and you can say from maximum efficiency data, let us first find iron loss and full load copper loss. So this is what you need to find. Once you know iron loss and copper loss, things becomes pretty straightforward. You have to just substitute the values of iron loss as well as copper loss. So fine, let us solve. At maximum efficiency, or in short, at eta max, what is that you are observing? Iron loss is equal to full load copper loss. So you can write the expression for maximum efficiency. So eta max is equal to SFL cos phi. I'm not taking x because I'm assuming full load condition divided by SFL cos phi plus iron loss plus iron loss. Why? 2 times iron loss, because in place of copper loss, I'm substituting the iron loss. Okay, so that is equal to, you can, okay, or that implies, okay, what is eta max? Is 0.9, which is equal to full load. Full load value is 25 kVA. So 25 into 10 to the power 3. Okay, so it is happening at full load. Yeah, so full load is 1 and UPF. So UPF is 1. Okay. Divided by, if you want, I will put X also here. Okay, X into SFL. Whereas X is 1 because they have given full load. So for full load, X is equal to 1. So in the denominator, you will have 1 into 25 K into 1 plus 2pi. Okay. So in this particular equation, only pi is unknown. So determine the iron loss. So we just determine the iron loss. How much are you getting? So are you getting iron loss as 255.1 watts? So iron loss is 255.1 watts when you simplify. Okay, so you have already at maximum efficiency, iron loss is equal to copper loss. So Pi is equal to PC full load is equal to 255.1 watt. Okay. So this is the very important data what we have found. So iron loss is equal to full load copper loss is equal to 255.1 watts. So that is the required loss data to proceed with the rest of the problem. Once the loss component is known, then you can start finding out the efficiencies sequentially, right? So first let us consider 3/4 of full load and UPF, right? So in the first case, you can write what is 3/4, 3/4 or 0.75. So X is 0.75 and UPF, so power factor is 1. Okay, so you can, I will write the efficiency relation here, so you can refer. So eta is equal to X SFL cos phi divided by X SFL cos phi plus iron loss plus X square times PCU. So this is the formula which I have written so that you can quickly refer while substituting the values. So let's find out eta. What is eta? X, which is 0.75 into SFL. What is SFL? 25. That is the full load rating of the transformer, 25 kilo into cos phi. So they have asked you to calculate the efficiency at unity power factor, hence cos phi is 1. Divided by plus iron loss, you have found 255.1 plus X square times the copper loss. Okay. So what is X? It is 0.75. So 0.75 square times the copper loss. Okay. And when you simplify, you will get the efficiency. So start substituting. You see, I'm using the calculator to find the answers so that even you will do the same thing. So that is 18,750 divided by 18,750 plus 255.1 plus 0.75 squared. So that's 143.5.
$97.9%.
Yeah. So eta, you will get it as 97.91.
Yes, sir.
97.91%. So that's your first part, 97.91%. All right. So similarly, you can solve part 2 and part 3. Okay, please do it. Okay, and let me know the answers. So part 2, let me handle now. I will just change the values on the board. So what is it given in part 2? Half full load and 0.8 power factor. So half of the full load. So that is X is 0.5. And what is the power factor? 0.8. So you have to just change the power factor value and X value. This is 0.8 and this is 0.5. 0.5 squared. $96.9. So for case 2, efficiency is 96.9. 96.9% you'll get. I have substituted the values. And then you can handle case 3. Just let me know how much you'll get for case 3. And finally, case 3. Okay, case 3 is pretty interesting. It is 1.25 times full load. That means to say you are going above the rating of the transformer. So rating is 25 kVA. So you are basically exceeding this rating by what factor? By a factor of 1.25. All right. So that is also possible. You can always do that. And in developing countries, you know, due to this overloading, in developing countries, you can observe this voltage fluctuation. Okay, you must have encountered the low voltage issues, right? So this low voltage issue is due to this reason as well. Okay, there are multiple reasons. So this being one of the reasons, that is loading the transformer beyond its rated value. That is one of the reason for low voltage issues in especially developing countries. And the third one, okay, so eta is equal to X is 1.25 into rating into cos phi divided by plus iron loss plus x square times the copper loss. So that is 1.25 square into 255.1. As you can clearly observe that copper losses are increasing with the increment in load. Okay, that is the reason, I was mentioning the maximum efficiency normally will take place slightly less than the full load value. So that's okay. 28, 125, how much you'll get?
97.73%.
Yeah, 7 to 73%. So that's about problem number 3. Okay. Fine. So I will send 4 assignment problems from transformer chapter. Okay. So I'll not give many assignment questions, only 4 I will give. So try to solve those assignment questions. I'll give about 3 days of time. Okay. So please solve those assignment problems. All right. So let me do one last problem. And you let me know about the values. All right. Fine. Copy the last problem. Take down a 600 kVA transformer, pretty large transformer. 600 kVA. So this is a power transformer. You can make out. Rating is very high. 600 kVA transformer has an efficiency of 92%. Has an efficiency of 92%, both at full load unity power factor and half load 0.9 power factor. Both at full load unity power factor and half load 0.9 power factor. So same efficiency is found at full load UPF, half load 0.9 power factor. All right. Determine its efficiency at 75% of full load and 0.9 power factor. Okay. So determine or find efficiency at 75% of full load, 0.9 power factor. This is the problem. So try to solve this particular problem. How will you solve? Write down the efficiency relation for two cases. So you take case 1, case 1. In case 1, X is 1 because full load and power factor is 1. And then you consider case 2. In case 2, what is the scenario? X is 0.5 and power factor is 0.9. So consider these two cases and try solving the problem. So I'll not write the efficiency relation, I'll directly solve because I've already written. So efficiency is 92%, so 0.92 is equal to X SFL cos phi 1 into SFL is 600 into 10 to the power 3 into cos phi is also 1 divided by 600 into 10 to the power 3 plus iron loss plus x square times copper loss. So x is 1, hence you will get PCU full load. Okay. So solve this particular equation. Okay, you cross multiply and you tell me what is PI plus PC. Okay. So equation 1. And then you can consider equation 2. That is for fresh set of conditions. Same efficiency under a different condition. So 50% of the loading. So X is 0.5 into VA rating 600 kVA into cos phi 0.9. 0.5 600 into 10 to the power 3 0.9 plus iron loss plus x square times copper loss. So 0.5 is 0.5 square is 0.25. So it is 0.25 into PCU load. Or you simplify, you will get it 0.92 pi. Right. So when I multiply 0.92 with pi, I'll get 0.92 pi plus 0.25 into 0.92. So that will give me 0.23. So this is 0.23 PCU equal to so it is 21.6 kilowatt. Solve the two equations that will give you iron loss and copper loss. So solving equation 1 and 2 gives iron loss and full load copper loss. So when you solve, you will get iron loss as 13.913 kilowatt and 38.26 kilowatt. All right. So please check. The iron loss 13.91 and PCU full load is 38.26. Okay. So having known iron loss and full load copper loss information, you can find the efficiency at this particular loading. Okay. So I'll give the answer. You can cross check whether you are getting this answer or not. So when you substitute, you are supposed to get the efficiency as 91.63. Okay. Efficiency, you should get it as 91.63. Okay. Please confirm these answers. Please cross check. Okay, whatever is factual, you write it down. I'm getting slightly different answers. That's the reason.
So 91.95%.
How much you'll get? 91.95.
95%.
Okay. What about these two losses? Did you get the same answer?
Yes, sir.
Yeah, fine then, fine. So, not agreeing with the book answer. Okay, nevertheless, I'll just cross check also. Okay. So, fine. This is 91.9 or 91.6, doesn't matter. Very closely. Okay. So that's it. So that is it from Transformers chapter. Okay. So what I will do today, I'll send some 4 assignment question. Please try to solve. And on Monday, 3:30, I will keep a revision class. So if you have any doubts on Transformer chapter, or if you want me to teach anything in Transformers, I can do that. All right. Fine. So that's it for the day. Thank you so much.